radius of an r 10 meters is fixed in space and carries a spherically symmetrical charge distribution. Now, that doesn't mean necessarily that the distribution is the same all throughout. It would help, in my opinion, for them to have a diagram of what they're talking about. But I guess that's part of the deal. The density, that's volumetric density, apparently is changing. Not only is the amount of that density changing, the sign of the charge is changing as well. So when you're at the center, you're going to have a density. As you move out, that density is changing, and the sign can change as well. So boy, oh boy, doesn't that sound tricky? They're also going to drill a hole through this thing. Let's just pretend, hey, why I can't grab that thing now? So the hole is going right down the middle. That line represents the hole. A small non-conducting ball carries a positive charge and is placed within the hole. So now this charge can be placed anywhere in the hole. The location of the ball is X. Now I am assuming that this X is measured from the center. The friction between the ball, no friction, no gravity. Okay, the graph shows the potential voltage, that's the electric potential, at points in the hole between the center of the sphere at r equals 0 and at the right end of the sphere at r equals 10 as a function of r. Let's just put in a little test charge. I'm going to make the test charge red. Here's the test charge. Now, I'm going to grab this test charge and I'm going to move it around. When the test charge is at the center, we have a lot of voltage. Oh, can't do it. I got to turn this off. And then I got to do this. Can everybody see what I'm doing here? Can you see the text I pulled up?
Yeah.
Okay.
It looks like a Pokeball.
All right. So when we are at the center, we have a lot of voltage. That means it's got a potential energy. It's got the potential to do what? To get kicked out. Systems in nature naturally go to their lower potential energy. That's a fancy way of saying water runs downhill. So this charge is going to naturally want to move outward. It reaches 0 potential energy about halfway. Now, if we released it from there, it's going to gain kinetic energy. But I don't really want to do that. All I want to do is grab it and move it around and see what happens. If I bring it up to here, the potential energy increases again. Now, this is an unusual looking curve, but we've seen stuff like this. A little like the bonding curve, where you reach the minimum potential energy and then you come back up and it becomes asymptotic with infinity. I did that in honors physics. I talked to you guys about that. What this means is to get from here to here, I have to do work. I got to raise my potential energy. So where does this thing want to go now? If I released it from rest here, it's going to want to come back. If it oscillated, it would oscillate about some minimum potential energy here. Now, I'm not saying that you have to have that whole discussion before you do the problem. All I'm trying to do is set my mind to looking at the thing so I have an understanding of what's happening. Let's get to the question. What is the furthest position from the center of the sphere from which the ball may be released from rest and exit the sphere? If I released it from the center, it has, tell me something. Wait, I better put a formula up on the board here. What is voltage? Potential energy per charge, right? The little q is this charge here. If I multiply that q by the voltage given on the graph, I'm going to get the potential energy, okay? This q doesn't change. So the potential energy is simply proportional to what I got on the graph. If I have a certain potential energy up here, and at the exit I have that much potential energy, if I release the ball from 0, do you think it's going to get all the way out?
Yes.
Sure, I got way more than I need. So they're asking us, where along here could I go to just barely escape?
At 2 meters.
R equals 2.
Somebody suggest an answer.
2 meters.
Yeah, 2 meters. Because now I have 60 units of potential energy. That's what I got there. It would just barely escape. That would be the answer. How do you justify your answer? You're going to have to say something about the energy at the end, and you have to start out with just a little smidgen more than that to get out, or call it equal. The ball is released from the position indicated in part A and exits the sphere. Describe the magnitude and direction of the ball's acceleration between 5 meters and 10 meters. So what do you think? You know, I think I better show you something else too. Voltage is equal to that potential energy could be considered a work per charge. You could also consider it to be a force times a distance per charge. Hold on. So if I rearrange this and I write voltage divided by X is equal to F over Q. Do you remember what F over Q is?
The E field.
Yeah, the electric field. The one thing that we don't have in here is the negative sign. Volts, that's volts, per meter is the same as the electric field. Now, why do I always put the negative sign in here? I'm going to draw you an arrow. Let's say we have an electric field that looks like, oh, that's the wrong arrow. Let's say you have the electric field going this way. If I move in the direction of the electric field, what's happening to my voltage?
It's decreasing.
It's decreasing, it's going down. And that's the idea of this negative sign. When you move, and that's the same thing for gravity. If you drop a rock, you're moving in the direction of the gravitational field, you lose potential energy. So as I move in this direction, my voltage is dropping. The force is in this direction from that field. So when I'm right here at the bottom, let me say it this way. Volts per meter would be the slope of this graph. Does everybody see that?
Yeah.
Okay, thank you, Addis. So the slope here is what?
0.
0.
And when you reach the minimum potential energy and you start to gain potential energy, the force acting on you here, this is the equilibrium position, you're at the minimum energy. So you can look at this in a number of different ways. The force is going to be 0. If the force is 0, what's your acceleration?
0.
0. What's your acceleration here?
0.
Yeah, it's 0. Now, as we climb up this energy hill, which way will be my acceleration? Forwards or backwards? I'm trying to get out of here. Will my acceleration be positive or negative?
Negative.
It's negative. So if we look at it from the slope, if we look at it from the electric field, you can say, yeah, the acceleration's got to be the other way. You've got a positive slope, so therefore you're going to have a negative acceleration. Another way of looking at it is just from the energy point of view. if you're going uphill and you're going uphill you're increasing your potential energy, you got to be slowing down. Your acceleration has to be negative. So I suppose you could talk about it either way, from an energy point of view or from a force point of view. Whoops. Okay, what the hell is all this about? Like, first of all, as soon as I see this and I see a student wishing to model the electric field, I really resent this. I don't give a crap what that student thinks. Like I was telling Dan this morning, they're putting the student in the position of the teacher to evaluate a kid's work. Who the hell would do that? I would. When we all sit around and we talk about lab work, and you're supposed to come up with an idea for how to do a lab. I think about some of the lab stuff that we've done where you're forced to not follow some lab sheet, but that's the spirit of all this. I just don't know if it's legit. I don't feel like this is really, I'm not comfortable with this whole format. It's an awful lot of pressure to throw something that's so unique or new at somebody in such a high pressure, short amount of time. So whatever, all I'm saying is I feel for you. A student wishing to model the electric field within the hole. Suggest this equation. Now they give you some numbers. Consider positive values of ER to be directed to the right. So the electric field. State one feature where it seems it's correct and one that's not correct. Let's plug the numbers in and see what we get. If A is 4 and B is 5, what would happen if R was at 5? Then what would this be?
The electric field is 0.
It would be 0. So what's 0 times A?
0.
I think that agrees with the conversation we just had. Your slope is 0. I don't think you're going to have any electric field there. There won't be any force on you. So that sounds right. But what about the sign? Like if I move over to here, then this is going to be a 5 minus a 7 is going to be a -2. Then this is going to be a negative electric field. You think that's correct?
Yes.
I think that's correct too. So then what the hell doesn't work?
Maybe the magnitude.
Give it a shot. What do you think? Talk to me about it. Who is that? Shivam?
Yeah.
Go for it, baby. I need somebody to step in.
So if like I plug in 10 compared to plugging in 0, those numbers, would we have the same electric field? I mean, looking at the potential energy graph, they're not the same, right? From at 0 and at 10.
Are you saying that if we plug in for R, we plug in a value of 0? Is that what you're suggesting?
Yeah.
So if we plug in a value of 0 for R, we're going to get 5 times 4. We're going to get an electric field of 20, right? Okay.
What about the fact that that function is linear and the voltage graph isn't? I mean, well, the derivative can't be of that graph can't be linear.
The derivative of this graph can't be linear. Yeah, I'll agree with that. More people are joining. Oh my gosh. Everybody, turn your sets off. Dean's coming on.
I was thinking that like at 0 and at 10, it's your electric field is going to be, it's according to the equation, be 20 for each. Wouldn't they be different?
Yeah, well, I was going to look at the slope again, like at 10. What's that slope look like to you?
0.
Yeah.
It looks like it's 0. Are we going to get that here?
No.
No.
No. So that's one thing that won't work. Yeah, I see what you're saying also, Malav. Now, let's point out, there's more than one right answer. Kids don't like that. They want to get the right answer. This is the same thing as we were talking about before, where they made you pick a resistor, and a capacitor. There's many combinations. So this is the kind of thing that you got to get used to. There's ambiguity in all of this. All right. The student checks their work, corrects their mistakes, and derives the correct expression for E as a function of R. The student then wishes to derive an expression for the charge density. Any idea what the hell they're talking about? I'll give you a hint. Have you, and listen, my idea may not be the best idea. Who knows how to calculate the electric field in general terms using Gauss's law?
Isn't it Q in inside and then Q of the Gaussian surface?
Q inside divided by epsilon
Epsilon
naught
Not.
Times the area.
the area of the Gaussian surface. Might this help us? What is Q inside? Won't it be the, we always would say it's the density times the volume. So they're asking, they didn't say use Gauss's law. So they'll leave it up to me to figure this out, I guess. If you knew what E was, this formula will work if the density was constant and we just multiplied by the volume within, within R.
You use rho?
Yeah, P is rho,
Oh,
okay? So yeah, tell me what we would do with this rho though, because that density isn't constant. What do we have to do?
Take the integral.
Right. So you're going to have to take the integral of rho as a function of R times the volume, and that's also as a function of R, right? Over epsilon naught times the area. Now, what the hell is the area? That's the area of the Gaussian surface, which would be, for a sphere, 4 pi r squared. Now, does it say that you have to do the math for this?
No.
I think all they want you to do is set this thing up. Yeah. Do you understand?
Yeah.
So sometimes I remember the way they had these things worded in older exams. They would say something like, set up an equation, but do not solve for such and such. So all they wanted to do was see the steps, because after that, then it becomes a calculus test, So sometimes they do that. I'm interested in knowing what you think about seeing something like this.
That wasn't that bad.
Well, in retrospect, but when you sat
Different.
down to look at it for the first time, did you feel a little uptight?
It's overwhelming with all the
I don't
just
think I
wall
can
of
do this in
text.
25 minutes.
Okay, so keep this in mind now. You're no different than the other kids across the country. The most important thing is to not panic. You need to draw a diagram to help you visualize what's going on. Some of you guys still just want to start writing down numbers and try to calculate something. Obviously, that's not going to work here. You need to do things that will break the problem down. Look for things that you do know. Like I said, okay, they got voltage. I'm not sure how this works. So what did I do? I wrote down an equation for voltage. And that sort of helps. Remember, you're trying not to get everything right. You're just trying to rack up some points. If you get 50% on these problems, you're probably going to be in good shape. So when you don't get stuff and you're totally lost, the worst thing that you can do is just say, oh, well, there's nothing else I can do. Because then it'll affect you when you try to solve for the other things, because your mind is so shot now. Any case, I don't know. I thought that was pretty freaking crazy. but that's the way they go. But the other thing I think is really crazy is, so let's say you do this problem and you do this problem. They're going to give you credit, college credit for 2 problems for a whole semester of class?
Yeah.
It doesn't make any sense to me.
Sounds good to me.
Yeah, but well, like, what if you screw up something in this problem and, like I say, you freeze up and you go, oh my gosh, but you might have been able to do fine on all the multiple choice, you know? I don't know. It seems
I'm pretty sure like they would let you retake it if you tell them you had some kind of problem. I mean,
I don't think they're gonna let you retake anything. I think this is it, baby.
Just don't cash in credits for this year.
Yeah, I just don't understand how a college can justify that they'll give credit for this. But enough beating up on the AP exam. Let's get to this one here. Did you recognize this? This is something you should have felt comfortable with.
yeah.
We did stuff like this, finding the internal resistance, right?
Mhm.
Mm-hmm.
Do you need a moment to read this?
Yep.
Okay, I'll let you just read it for a couple of minutes. Just read that. Tell me what you think. I'll be right back, okay?
Mm-hmm.
I guess that was your cue to shut up, huh?
Yeah.
I gotta tell you what I think about this home instruction stuff. If we have to do any of this next year, I swear I'm gonna wanna have class on a regular schedule and everybody shows up and everybody's gotta turn on their damn camera so I can look at their faces. I wanna have 2 screens. I wanna have a screen to teach on, like a blackboard, and another screen where I can look at everybody's face, because that's human interaction. That's normally what you do. And I think this is a bunch of nonsense. So anyway, you can tell I'm in a really good mood this morning.
What happened?
Did you sleep?
Oh yeah, I did. I slept a little extra tonight, last night.
Hooray.
I got to tell you what happened yesterday in honors physics. I should do the lesson with you. I went to the University of Colorado website, and they have all these simulations there that are pretty good. And one of them was on the photoelectric effect. And it's a little like that Millikan oil drop experiment. It's got metal plates and electrons running around. It's really pretty cool. And I collected data with a few kids, and we looked at the graph and calculated some neat stuff about the photoelectric effect. So that worked out great. I was very happy about that, especially that only a couple of kids did it, because I didn't want to talk to the rest of them. All right. Yeah, too many of them. I don't know. Everybody's distracted with everything else. They have a hard time concentrating. But nonetheless, let's get back to this. You're going to make data in a graph for this. But before I did that, I just thought to myself, maybe I ought to label the diagram. Did anybody think about doing that? I gotta move this out of the way. What are we gonna call this? How about
Capital R.
capital R? What do you want to call this guy? Lowercase r. What do we want to call this thing?
B.
Now, I don't have a script E. So how about if I just write EMF, okay? What are we going to hook up on this thing to measure stuff with? What letter would you want me to put inside here?
An A.
A.
Yeah, A for amps. We're going to measure amps. And now I'm going to hook up another meter. And I suppose you could hook it up here, or you could hook up over here. It wouldn't matter. You're going to get the same thing. What am I going to measure over here?
V.
Yeah, volts. So just in describing everything, you're going to get points. You know, like even if you don't know what else to do, you're going to get something. What can we say about this formula? V equals IR. What R am I talking about when I use this formula?
The external resistance.
Yeah, that's the one that I can measure. The formula actually does apply to this formula. to this resistor here, but that's not the one that I can measure directly. This voltage is the voltage drop across any resistor. I gotta turn this off to click that off.
So why couldn't you do it for the other one?
Well, all I'm saying is you can. I'm just saying that you can't measure the voltage across this resistor directly, can you?
Yeah,
You realize the battery is this whole thing. You can't get inside the battery and measure the internal resistance. So from an experimental point of view, we will apply this formula to this resistor. Theoretically, you can apply it to this one if I only knew the voltage drop across that resistor. Did that make sense?
Yeah.
All right. Well, anyway, I'm going to know R. I'm going to know I, because these things I can measure, right? Is the capital R, is that something that we know is laying around the lab? We can get those resistors and just know them?
Yeah, I think.
Yeah, I guess so.
A variety of resistors. Okay, so let's say we know that. So that means we're going to know the voltage drop across here. Now, could we use the same formula to calculate the internal resistance?
Yeah.
We're going to say that,
Delta V.
yeah, okay. I don't have a delta, do I? A delta V. The change in voltage across this thing. Actually, that's not what I want to do. Hold on 1 second. There's something else I want to do. I want to disconnect the circuit and just measure the voltage on the battery. If I don't have a connection, my EMF is going to be equal to the voltage terminal. You remember calling it terminal voltage? You don't know that.
No.
Okay, the terminal voltage is the voltage at the terminals of a battery. It's not like it's terminal velocity or anything. It's the voltage at the terminal of a battery.
Got
If I disconnect this thing and I have no current running through here, how much voltage will be lost across this resistor?
All of it?
the terminal voltage.
How about none of it?
None of it.
Damn.
Yeah, watch. If you take this formula that we all know and love, I feel like I'm not doing a great job on this, and I'm really sorry. Voltage equals IR. If I use the little internal resistance in here, and the circuit is broken, the current is 0. So what is the voltage drop across this little resistor then?
0.
It's 0. So if I have no voltage loss across here, and I hook my voltage meter up from one end of the battery to the other, then the voltage reading on this meter is going to be the EMF voltage.
Oh,
No?
I see that now.
You see it. Okay, great. Okay. So that means I'm going to know what the EMF is. So could I go around this loop and say actually, I see they have the positive end over here. I'm going to gain voltage from the battery, the EMF. Then I'm going to lose voltage across this resistor. And then I'm going to lose more voltage, and I got to get back to R. Do you remember that when you go around a loop, all the voltages add up to 0?
Yep. Yep.
Okay. All right. So let's put in the EMF. Then the current's going to come out through here and go down here. I'm going to go subtract I times capital R, right? Now I'm going to subtract I times little r. And that's going to be equal to 0. The voltage from the chemicals minus the voltage lost across here minus the voltage lost in the internal resistance is equal to 0. Does anybody see what I'm doing?
Yeah.
So we now know what EMF is. I can measure the current. I know what the resistance is. I can say that's equal to I times R. I can go EMF. I'll put this in parentheses. EMF minus IR divided by I equals the internal resistance. Now, I'm going to tell you, this is what we did in class. We had to measure the internal resistance. The trouble I'm having now is they want you to make a graph. What the hell am I graphing? They're going to change. We have the ability to change the R, capital R. If we change capital R, that's going to change the amount of current going through this circuit. But we should still get the same internal resistance. Does that make sense to anybody? I think I've lost everyone.
I
You're
might.
good.
But if you like graph it, it'll just be
It makes sense.
a line.
Well, help me figure this out, because honestly, I looked at this morning and I said, I'm not even sure what I'm graphing.
They just say y-axis. That's
All right, well, let me tell you this. Here's an idea. If you use this formula, and I just had an ability to measure the voltage, I could change the voltage across a resistor, right? If I could change my voltage and keep the resistance constant, my current is going to change, won't it? So what if I made a graph? Voltage versus the current. What would that graph look like?
Straight line.
Line.
And what would the slope of that line be?
Internal
The
resistance.
resistance.
It would be R. Now, you called it internal resistance, somebody. It doesn't, this is just a resistor. I don't know. And I have a power pack that I can change the voltage for. This is the kind of thing I think they want you to do. And then I think what they want you to do is say, okay, so the slope of this graph is going to be some way of calculating this internal resistance. I guess, I mean, this seems silly, but I guess, could I do this? I don't know.
So would it just be EMF minus IR on like the y-axis and then I on the x-axis?
Yes. Well, would that be able to get you the slope of the slope being little r?
Yeah.
Okay. You know, I don't think I would have done that in lab. I think I would have just calculated little r a few different times for different capital R's. But in lab work, they always want you to make a graph and look for a trend, draw the best fit line. You know, we've talked about that. Well, listen, this is gonna be over in about a minute and a half. I want to get back on, if you don't mind. Where's my clear my drawings? Oh, down here. I moved it. And now I'm going to turn this off. Okay, the last part is they're talking about error. And they realize that, oh boy, we forgot to include the resistance of the wires. If you forget to include the resistance of the wires, what would that do to your load resistor, as they call it?
Which one's the load resistor?
The big boy.
Oh,
They call that the load resistor or the external resistor. You thought you had 10 ohms because that's what you plugged in. But actually, you probably had 11 ohms because the wires have resistance and you're ignoring that.
so now the current's lower.
yeah.
No, wait a minute. Well, the current, the current is this is all from the experiment, you know, like the current didn't change.
But doesn't
Does
something else have to change too if the resistance changes?
Yeah, it's going to be this guy. You thought that you had a certain internal resistance,
Oh,
but
okay.
you were looking at this as if you had, like, let's say you have more people. The Bryson bad boy is coming back in. Yeah, this is a pain in the ass, huh? Okay. So if you wanted to say you had 10 ohms here. Uh-oh. I don't know why it does that sometimes. Isn't that weird?
What's it doing?
It's beeping and it won't let me type, but it's letting me draw. I don't know. So let's say you thought you had 10 ohms here, and because of that, you calculated an internal resistance of, say, 1 ohm. But it turns out that because of the wires, you have 11 ohms of resistance. Some of the resistance that you were attributing to the internal resistance is actually due to the wires. So what do you think is going to happen? You think your conclusion here is that this resistance internal is probably less than what you were thinking. Did that make any sense?
Yeah.
All right.
It
I
would
think,
become less or more.
well, hold on. I got to go add more people.
Because don't you have EMF minus I big R over I equals little r?
Let me get the formula back up there.
Oh wait, that minus a bigger value makes it small. Never mind.
Yeah?
Yeah, I see it now. Because yeah, I'm good.
So let me just rephrase it in plain English here. This internal resistance gives us a lower current than we would have if there was no internal resistance. If you didn't have any internal resistance, you'd have more current. So some of this resistance here, I'm attributing that reduced current to the internal resistance, when actually that reduced current is also attributable to the resistance in the wires. So if I have more resistance in the wires, I'm not going to have as much resistance in the internal resistor. Let me turn this off and see what else is cooking here. Okay. Well, there you have it. I think the whole damn thing is crazy, but like I say, you've been through an awful lot this year and last year. You've seen so much stuff. Just don't let it rattle your cage. Take it slow. Just jot down a basic formula. Like up here, what was the basic formula I wanted to write down? Voltage equals potential energy per
E
charge.
over Q.
That got me started. Down here, the basic thing I wrote down was voltage equals IR. You got to start somewhere. So you start with the basics. And that might help you. Hisham already have him. Okay. All right. Does somebody have a question? Because some of you have been looking at these problems.
Can you scroll down to part E? I just want to see the question.
I'm sorry. Can you speak up?
Can you just scroll down to part E? Like I want to see like specifically what it was asking.
Yeah.
Oh, okay. Yeah, I got it.
Do you notice that they're not asking you to derive an equation? They're not asking you to calculate anything. So it's just a description. That's why I'm looking up here saying if you attribute your internal resistance, if you find out that there's more resistance out here, then there's going to be less in here. I think that's a simple explanation. And they're not looking for a whole bunch of math. All righty. What should we do?
Cry.
All right. I'll give you something to do if you I sent you some problems, right? Actually,
aren't
do
the
you want to
mechanics-
just go right now and talk about the mechanics problems? Because I
Yeah.
already did that this morning, but I can do it again.
Yeah, can we do mechanics?
Yeah, we're gonna get the mechanics going. What am I doing here? Hold it. I'm gonna go get to your link, Addis. What the hell is this? I clicked on the wrong thing. Inbox. Let's go. Oh, for God's sakes. Where is it? Can everybody see this?
Mm-hmm. But I have it pulled up on the side too.
When I first looked at this, I thought, what the hell is going on? This looks like a model rocket with a flame sticking out of it. And it was blowing exhaust on this thing. What a bad idea that was. So right off the bat, I've got a bad mental picture. It says a constant force F is exerted on a dart of mass M. So this little thing here is the dart in the horizontal direction as it moves through a tube of length L. After exiting the tube, the dart collides with the box of mass capital M and sits on a table. The coefficient of kinetic friction between the box and the table is μk. The dart block system then slides across the table and comes to rest after traveling distance d. This is just the kind of problems we've been talking about. You've seen stuff like this from me. How many times have we had a spring or somebody pulling and the box has to go a certain distance and stop over the friction? That's not bad. This also involves a collision. Hey, we've been doing them too. So I thought this isn't too bad. Students experiment with a variety of tubes, assuming that air resistance is negligible and that all other parts of the experiment remain the same. Should the students use a long tube or a short tube to make the stopping distance the longest? So why don't you think about that just for a second? Read this again, okay?
It says that the pressure is only happening while it's in the tube, right?
Yeah. Sydney just joined us.
Should it?
Sydney,
not
are you there?
matter?
So then it should be shorter because there's only pressure.
No, it should be long tube because it says the constant force F exerted. As long as
It's trying to make it go the furthest. Okay, yeah, then it's longer tube.
Wouldn't it not matter if it's constant though?
the longer you're in the tube, the more force is applied.
No.
Yeah,
The same force is applied.
It's just the same force no matter how
Like,
long
but
it
it-
is.
Say it right. The longer you're in the tube for, the force is the same, but what's changing?
The distance.
How close you are to the block.
How
The amount of
about-
work done to the dart.
Who said that?
Me.
Below.
Malav. Yeah, force times the distance, right? Work equals force times distance. So you don't want to say it's the same force. It is a constant force, but you're increasing the distance. And so if you increase the distance, you're increasing the work done. Hello?
Yeah.
So you're giving it more energy.
That's right. All of that work is going into kinetic energy of the dart. Do they really want you to go derive an equation for how far the block goes? For
Like-
part A?
No.
No. This could be very confusing. You could waste a whole lot of time trying to derive that formula and it won't matter because the constant friction, all of that stuff's constant. The only thing changing is how fast this dart's coming out of the tube. So all you have to do is just say, you want the dart to go faster? More distance gives you more work. So it'll have a higher kinetic energy. Does that make sense? So now I know kids say sometimes, oh, I thought the problem was way harder than it was because you gave us all that extra information. This is an example of what people do. They give you more information than you need, and that's life. Okay. So let's take a look at the next problem.
Wait, so how would you justify your answer though?
Just, I already wrote it. Work
Okay,
equals 4
just
times
that?
distance.
Just
I'm
that?
telling you, that's all you need to say. What else would you need to say?
I don't know.
If you increase the distance, you're increasing the velocity of the dart. The more the further this block is going to go, just due to the. I mean, I guess you could start talking about all the waste heat and everything else, but I don't think you need to. Students derive the following equation for the stopping distance. I like it. Somebody else is going to do this dirty work, not us. But it says, without algebraic manipulation of the equations, explain whether this equation accurately matches your explanation in part A. Look at that and tell me what you're thinking.
It's a lot of letters.
Who said that?
Bryson.
Now, what did you say, Bryson?
It's a lot of letters there.
Right. It's done intentionally. Is mu k constant?
Yeah.
Yeah.
Is G constant? Is capital M and lowercase m constant?
The whole bottom's constant.
Yeah. Then all they want to know is, does this equation work for what we set up here?
Yeah, because the longer the L, the more distance you get.
There you go. That's it. All you have to say is, yes, it works because bigger L, bigger distance. Don't you think that that's like deceptive?
Yes.
Yeah, people are going to be spending 10 minutes trying to figure out if this formula is right. All they want to know is, does it agree with what you said? And that's it. Okay, now students then change the force so that it can be described as a function of position. What do you think X is? They didn't say what X is, and I swear I know kids would get points off in a college lab if you didn't define what X is. What's X? Okay, don't talk to me. I think X has got to be how far the dart has traveled down the tube.
Yeah.
As the dart goes down the tube, the force is increasing. Do you agree with that?
Mm-hmm.
I just think that they should have told you X is measured from the left end of the tube. Okay, explain how the student could use the equation given above to find the launch speed of the dart if the length of the tube is 2 meters. What do you think we're going to do?
Take the integral from 0 to 2 of 12x.
Okay, you could. What's work? Force times dx. Integral. Does that make sense?
Yes.
Okay, nobody sees that?
Yeah.
Yeah.
Okay, so, you could go ahead and take the integral of that. Or, whoops, could you draw, see, there's no absolute way of doing these things. I suppose there's more than one way of doing it. Could you look at a graph of force versus X? What would this plot out to be?
A linear line.
The linear line
And then what are you looking for?
Very end of the graph.
area. From
The
0 to
area, right? I mean, maybe I'm only going to here for 2 meters. Then this area is going to be that force, which would be 12x, right? It would be 12 times 2, divided by 2 to give you the area. But what are we trying to solve for? We're not trying to solve for the work, are we?
Well,
Set that equal to 1/2 mv squared.
There you go. So we're going to have to set this equal to 1/2 mv squared. So the work would be equal to and I had that before, right? So this wasn't too bad. Predict what will happen to the launch velocity if the length of the tube was doubled. Now we're going to go to 4 meters. I'm going to be all the way up here. If I double this distance, what do I do with my force?
Double.
It's double. But I'm not really looking for that. I'm looking for the area. What's going to happen to the area?
Quadrupled.
It's quadrupled, isn't it?
Quadrupled.
Yeah. So my initial reaction was, well, if it's quadrupled, then my velocity is going to be quadrupled. But is that true?
No.
No, 'cause-
If the work quadruples, this is a squared function, isn't it?
So it just doubles.
That's right. So the work would be equal to 1/2 12x squared. And then that's going to be equal to 1/2. I'm running out of room here, ain't I? mv squared. Now, we saw this in one of my last problems with a spring, that if you double the distance of the spring, you're doubling the velocity because there's a square on both sides.
They have the formula derived in the next question. I don't think you have to.
They do. Students are given an equation for the launch velocity. This. Does this formula justify our answer? Yeah, it goes with everything we're talking about. Could you take this L and bring it out?
Yes.
Then it's just going to be V is proportional to L. Okay, Sydney, are you ready to go on? All right. I love this system. You want to take a minute and read this?
Yeah.
Moab, did you already do all these?
No.
Okay. I thought, didn't you ask me to look at something like this like a couple weeks ago?
Yeah, I didn't know how to do this one.
Okay.
I looked at it, but I answered like a few parts, but I didn't know how to do the whole thing.
Okay, fine. All right. I'll let everybody look at this for a second. I'll be right back, okay? Ah. Can somebody tell me what they think of when you see a cart on a spring like this with a ramp?
Simple harmonic.
That's just what I thought of. And the first thing I wrote down was the period is equal to 2 pi square root m over k. And then you look down here and you say, great, I know what k is, you know? I could easily get the mass if I don't, because they let me use my lab equipment. I could put it on a scale and weigh it, right? But what are we trying to measure?
G.
Yeah. Now, do you see how hard it is to find? There's a lot of words here. So I find this, you got to take your time and break it down. There's no G in this formula. Plan B. Can't use this. Somebody have an idea?
F equals negative kx.
That'll help. That'll be part of this. What am I drawing?
Free body diagram.
Oh, yeah. And even if you don't know what you're doing, you can still draw a free body diagram. And then the next thing might happen, Sometimes I like to think of this as crossing a stream, and you have to step from one stone to the next. But it's pretty wide, and you can't always see the exact stone to step on all the way across. So you go a few stones out, and hopefully then you'll see the next one. If I draw this, can somebody tell me what this force is going down the hill?
mg sine theta.
So mg sine theta is this force.
So we're allowed to know that without knowing G? Like we can say that?
Who says we don't? If you are trying to find G, we need an equation with G in it. So that's going to be my unknown. You follow me?
All right, yeah.
Now, what's going on going up the hill?
F equals negative kx.
Yeah. I'm not going to bother with the negative sign, okay? All I'm going to say is, at some point here, the forces going up the plane have to equal the forces going down the plane if I just let this thing come to a rest, at equilibrium. So you see how sometimes, you plan A, plan B, and you just start writing stuff out. Can I measure X?
Yes.
It's in a lab. I can measure X. They tell me I know what K is. Could I measure the mass of my cart by getting out a scale and weighing it? Yeah, sure. Could I get a protractor or rulers and measure the angle?
Yeah.
Then I can solve for G. Once again, you could solve for G. How would you know how to measure what X is? You'd have to take the cart off, and they're going to want you to say that. You see, you can't just say measure X. You're going to have to tell people what X is. In other words, take the cart off, have the spring come to its natural length, put the cart on there, and measure how far it goes to this equilibrium position where it comes to rest. Okay? But you don't need to make a graph. You could just calculate G. But that's not what they want. And why not? Because it's only one measurement. What else are you going to do then? What could you change?
The mass on the cart.
Well, maybe you could, but honestly, they didn't say that we had more masses. They
You
said
can change the theta, which will also
Yes.
change the distance of like
yes.
X with the spring.
I would change the angle because they say I have to use this equipment. I would imagine that if you said I went and got more masses and had this thing come down, that might be a legitimate answer. But I'm going to play it safe and assume that they were not allowed to use any other equipment. They said we can take other things to measure with, but not other equipment. Hey, I imagine if you put the masses on there, you're going to still get points. What graph am I going to make then?
M sine theta versus kx.
Yeah, you know what I'm thinking? How about we do m sine theta on this axis?
Yeah.
Does that make sense?
Yeah.
Okay. So if I just did sine angle here, and up here I wrote kx over m, will I be getting a linear equation? No?
Yeah, you should be.
And then what would be the slope of that line?
G.
Oh my, look at it, it's all over my
West.
screen. Okay.
What was that?
What do you think of that? Nobody wants to make a comment?
It makes sense.
Seemed doable.
Okay. I didn't think it was that bad, except that, you You could get distracted by thinking about stuff like this. Do you remember that we did some problems where we talked about making graphs where you had to square something? We've done that a few times, haven't we? I'll show you what I mean in a minute. Okay, so that's it. That's the whole problem right there.
There's another part.
Oh, I forgot. Yes, there is another part. What the hell is this about?
Now you might be able to use the period thing.
Oh, you recognize that. Very good. Period is equal to what?
2 pi radical, what is it? K over M or something?
You
M over K.
You better remember this, okay?
Yep.
Now, you could always test it because kids get this backwards all the time. If you had more mass on the cart, it would have more inertia. If it has more inertia, it's going to be harder to move. It's going to take longer to go back and forth.
Okay.
Would you like that?
Yeah.
Okay. Conversely, if you have a stiffer spring, it's going to go in less time. Stiffer means it gets pushed back quicker. All righty. I did not like this graph. Because just up above, they said that friction was negligible, didn't they?
Mm-hmm.
Is friction negligible?
No.
Do you know what we call this? There's a name for this. Why the word damped?
Because the amplitude decreases for
That's
every.
because of friction. That's the damping effect. Is the amplitude dropping significantly?
Yes.
Yes. If I had a pendulum and I pulled the pendulum back and I let it go, would we expect to see that pendulum's amplitude drop by more than 50% in 1, 2, 3 swings?
No.
No, no way. Those pendulums go on for a long time, and people always ask me, they say, oh, is that going to go on forever? Well, that's why I don't like this, because somebody may have studied damped simple harmonic motion. And this involves more complicated equations. It actually has an exponential decay to it. So they don't want you to know all of that. So I think they should have just given me a graph that's had a more constant amplitude than this big drop off, because that to me is a big distraction. And I'm going to tell you more about that in a minute. So what would I look at on this graph to use this formula?
What the period is for each
Yeah.
oscillation. But how would you figure that out? I don't get it with this graph.
Okay. What's on here?
Time.
Time. This is the position. If I'm at the 50 centimeter mark and I do this, I'm almost made it back to the 50 centimeter mark. Now I start to go back down again. Have I completed one cycle?
Yes.
Well, then what do you call this amount of time?
Period.
What's the period?
1 second.
And what's the, oh, I gotta turn this off now. What's the period for the second cycle?
1 second.
What's the period for the third cycle?
1 second.
Now, in reality, the graph probably wouldn't look like this, and I'll tell you more about that later. What would you want to do as a good student in laboratory technique? Would you just look at one period?
No.
What's the best technique?
Average.
Take a bunch and average them.
Right. Go do 3 periods and divide by 3. It just turns out that each period is 1 second, and it's damn well lined up really good here. If they give you data where there's some error in it, make sure that you do the whole graph and divide by the number of cycles. And that's what I've always told kids, whirling a string around your head. Just don't time one thing, time 10 of them and divide by 10. So we know that. So you take the period, you put it in here, and what are we solving for?
M.
M. They want you to know how can you get the mass. That's how you do it. Using simple harmonic motion. Now, in retrospect, you look at this and say, oh man, that was easy.
Yeah.
Yeah, that's the way it always is. But I would like to point out now that if you do study damped simple harmonic motion, you're going to find out that the period actually changes with amplitude. Isn't that crazy? Didn't you learn in simple harmonic motion that the period is independent of the amplitude?
Mm-hmm.
For
Yeah.
small.
Okay, were you about to say for small amplitudes?
Mhm.
For small angles.
Yeah, well, listen, that's true for things that don't have a linear relationship. If you did force versus X, and your graph looked like this, then yeah, that linear relationship starts to break down, okay? But what if it was truly a linear relationship all the way through? What if you had an incredible spring that was just 1/2 kx squared for the potential energy and F equals negative kx and it was constant? The amplitude will not affect the period, okay? But if you add some friction, the amplitude starts to decrease. So your natural inclination would be to say that if you have a smaller amplitude, the period won't change. But in fact, because it's the friction that's making the amplitude smaller, that slows it down and the period starts to get longer. Isn't that crazy? It's not the amplitude that's affecting it, it's the change in amplitude that's affecting it. So it turns out if you study damped simple harmonic motion, this period is actually going to get increase as we go down this scale because the friction keeps slowing it down. What do you think?
Fun.
Yeah. Okay, well, anyway, that was more than what they expected anybody to know. Obviously, this is just fine. Just get the period right off of that thing and plug it in. Now, Sydney, you asked me if when you were doing mechanics, we're doing mechanics. Do you have any questions?
No, I'm good.
Well, swell. Are we going to have a moment of silence now?
That was a lot.
Okay. I'm going to go to my whiteboard. No, I'm not. I got enough white right here. I sent you some electrostatics problems. And then I sent you an update that says, forget them. We're just going to talk about what Addis asked me to talk about. If we're done talking about these things, we ought to talk about those problems. I'm going to get on later. I don't know when. I don't care. 4 o'clock, 8 o'clock. And I'm going to have to say a few words about them because I think they're good problems. I'm going to show you a little bit about it. There's a charge. It's moving this way. Q. Okay? We got a target over here. That's going to be capital Q. If you know this incoming velocity and you know where you're starting from, maybe we're starting from really far away. Let's assume we're starting from really far away. So R is going to be infinity. Would you be able to predict how close this charge will get to the target? The target can't move. What technique might you apply to this?
Energy?
Yeah. So this involves mechanics and electricity together. I kind of have a feeling they're going to put something like this on the test. I don't know why. I see the connection, you know? So, okay. Now, the target doesn't have to be a point charge. The target could be an infinitely long line charge. You get it?
Yeah.
Okay. The target could be a plane. In each case, I want you to calculate how close this thing's going to get. I have to go back and change, I think, one of the problems in terms of where it is for the initial. Like, for example, if you have a plane and it's infinite, won't you have a constant electric field for this thing to fight against? Somebody say yes.
Yes.
Okay. So could I start this point charge off at infinity to shoot at this thing?
Yeah.
It won't work. Because if I start it off at infinity, I'll never get the charge to get anywhere near this thing because it's got to fight this constant force way the hell out there. You have no idea what I'm talking about?
No, I hear you now.
Okay. So whenever we have something like this, I'm going to have to tell you we're starting at a finite location, and then you're going to tell me how close we're getting. Now, you might be wondering, so why am I making a big deal about this? Because this is what people do in particle physics. How did Rutherford know what was going on with that gold foil? He took alpha particles and bombarded the gold foil, and he was able to do things like calculate the density of the charge by the way these things were deflected. Well, we're not doing something that hard. We're doing something pretty easy. It's coming in and bouncing straight out. So it's going to come to a stop, and we're going to calculate how close they are. But this is just what they do in particle physics. If you want to know how big a subatomic particle is, you bombard it with something of known energy and known mass and known velocity, and you try to measure how close it is, how close it could get. So there you go. That's a related problem. So I'm going to change one of those distances I think I have to fix, and then I'll send it out again. The other thing I wanted to do was go over the formula sheets. Did anybody look into that? Are you getting a formula sheet?
I don't know.
It's open book. You can use whatever you want.
Okay. Well, then we ought to definitely go over the formula sheet. What would be the easiest way for me to go find a formula sheet?
Look up
just
AP
search
exam
AP
formula
physics.
sheet. It'll come up.
AP
This is
Physics
going
C
to go
formula sheet.
away in about a minute. So I'll look that up. You look it up, and we're going to go over those formulas later. When do you want to get back together again?
After
As
4.
late as possible.
Yeah, as late as possible.
Okay, so Malav, you said after 4.
Yeah.
What's good for you?
5, 6 is fine for me.
Okay. So if
I
I
can do
get
later
on-
if anyone wants.
Yeah.
Well, are you okay if we just don't meet again till like 8 o'clock tonight?
Yeah, I'm fine with that.
Okay, fine. Then we'll meet at 8 o'clock tonight. Bye, everybody.